Hello guys, welcome to yet another tutorial for the Jeff rig. Now we're gonna move on and keep doing some more on the leg, which is the stretching. Uh, Now why do you need stretching is because we want to actually apply the rules, one of the rules in animation principles, which is stretching and squashing. And it's not just for bouncy ball, it actually is for a lot of things like character when you are doing the jumping of a character, or it is giraffe, right? Let me actually, I haven't hooked it up with the body yet, but when you go when you do the oh, doesn't work that way. Anyway, so when you're doing the let me do the whatever. When you're doing the jumping, right, the foot goes down. Let's just imagine that the body is going down. So you're doing the squashing part, right? It goes in, and when you're jumping out, you make it stretching up, and you may want to keep the leg on the ground for even a little bit longer while the body is going up, so that the leg is becoming longer, stretching longer, so that you can have that bouncy rubber band kind of like effect on the character, so you get more fluid animation. It's also partially like delays of the body parts, overlapping action, kind of like concepts. So you can, if you can have that, the character's movement will feel that much more fluid and vivid. So let's learn how to do that, okay? And so what you want to do is bring back the joints so you can see those guys. We're gonna apply that on the AK part, which is this guy here. This is AK part. All right. So for the leg to be able to stretch, first thing we need to know is how long it is. So let me go ahead and isolate the leg here, and using the create curve 2 and CV curve 2, I'm going to use one linear here, holding down V button, click on the first joint, second joint, third joint, and then the last joint that goes through this entire joint chain. That gives me a curve, right? And this is actually representing the length of the leg. I'm going to rename this curve, curve, left back, leg, original, length. Okay, so this is the length here. I'm going to go ahead and calculate or get the length actually in node editor. It's going to be underneath the window, node editor here. Let me go ahead and create a new tab and drag that in. I can actually double click to rename the tab just leg stretch, or leg stretching for now. And I'm gonna go ahead and kick this guy out and grab this guy, and I'm gonna measure its length using the curve info node. Oops. Curve info node, and I'm gonna rename this guy curve info left back leg original length. Okay, and I need to press 4 button to show me the input, and I'm gonna connect the word space 0 to the input curve. Okay, it's gonna be this, right? And that arc length now shows me how long the leg is, right? When it becomes straight, or the length from the first segment, the second segment, the third segment, add them together, how long they are. All right, so I got one length now. Another length I want to know is the distance from my pelvis joint to the controller, this distance. And that's going to be involves another tool that is going to be called the measure 2 here underneath create, measure 2 distance 2. I'm going to do that. Okay, and I can, it will ask me to click to pick point to measure. I can click on the ground 1 and 2 just to create it. Just to show you how this is, this is basically telling you the length or the distance from locator 1 to locator 2. Can drag either one, and it's gonna constantly updating the length, so that if this is here on the first grade, and it's gonna be on the on the origin, and you can see that the length is 1, right? Because that's how the length is. Alright, so I just to make them follow two things. The first one here, this guy will follow the first joint. I'm gonna use my driver joint, this kind of spring driver joint, grab that and shift select the locator 1, right? And I'm gonna do a constant point that's gonna make it follow right there. Okay, and then the other guy will follow the controller. So I'm gonna grab the controller and then the locator again. I'm gonna do the other locator and do point constraint. So now I have you know, two locators. They're constantly following my controllers and the hip, the pelvis joint, so that it's always gonna tell me what's the distance from the pelvis to the controller. Let me do some renaming. This guy is gonna be locator left, back, leg. This is gonna be the pelvis, and the other guy will be the ankle or controller, whatever. Let's call it ankle. Makes more sense. And the distance dimension will be renamed to distance dimension left back leg stretch. Okay. Alright, so let me go back to the outliner. You see there's a few things being created here. All I need is this guy. So I can do this little trick, grab those guys that I want to reserve, my curve info and distance, P them, and then I clear the graph. It's gonna keep those guys there. Okay. So this is now the distance. And I'm gonna use those to calculate the difference, because what I want to happen is when I drag this down, I want the leg to stretch becomes longer and make the ankle exactly still on where the controller is. Okay, so I need to stretch them, and of course how much they being stretched will be depending on the length of the leg and the distance here measured. So what I'm going to do here is using some divide. It's just like stretching the spine now. I need to use multiply divide here. And let me rename this guy, multiply divide, left back leg stretch. And the calculation will be we're dividing the distance here by the original arc length, so that I know that the leg is now this long, right? It's straight now because it has to when I drag the controller further away. So this is this length, this guy here. This length, or input 2x, is basically this length, and then the other length, this distance, is this length. And you can see now there's a difference, and I just need to scale my joint the amount, the same amount of this calculation here, because that's the ratio, right? That's the proportional ratio between those two lengths, and that's how much I want to scale my joint. So let me go ahead and grab my bending joint, and because that's the only joint that is deforming my skin, I need that to be stretched. So grab those 3 joints, so 1, 2, 3, and add these guys into the graph. So also pin this guys and pin the multiply divide, so I can just clear the graph. Okay. So what I need to do is connect just a very simple connection from the result of the multiply divide, which is output x, to the scale x of the joint. And let's do that. Now you can see they're getting crazy. The reason being is because my multiply divide is now multiplication. Let's change that to divide. So they're doing the right thing. Now you can see that the leg stretches, and it stretches exactly to the point of the controller. Now you can see the ankle joint is now on where the controller is. Alright, so that's the first or basic theory or workflow that you do for stretching. But this is not actually perfect. If you go ahead and take a look at how when I move the controller, when I move it in, it also stretches in and gets smaller. Right. Now the reason being is very simple, because when you drag it and make it smaller, this distance gets smaller than the length of the leg. So it basically keeps the leg's length as the same distance here, right? And that's not good. So how can I prevent that? Well, if you really think about it, it's a very simple concept. when the leg is, you know, getting to its original length, you don't want it to be keep shrinking, right? So you just want it to be 1. Okay. So there are multiple solutions here, and let me show you one of the solutions I have learned. You know, in my education, which is gonna be, you know, just use a conditional. Because I really want to show you what condition is. A conditional basically uses some condition here, first term and second term, to determine which one to export or pass out as the out color here. So I'm going to do some calculation here. So I want to compare the distance here. That the first term will be my. Let me actually show you how this works, so it's easier to understand what this is. I'm actually going to connect the output color to something. Maybe I'm gonna do a cube here. Oops, where is it? It's not showing up. Don't know why. But yeah, let me do a cube and make it bigger. Oh, now it's there. So what I'm gonna do is I'm gonna use this condition to control the cube's translate x, out color to translate x. Okay. So for now, the out color and input color R channel is 0 and 1. I'm going to change color if true to 10 and color if false to -10. Okay, it's not even enough, maybe 100, so we can see the difference. Okay, so how this works is that the output R color could be the color if true, and it also could be the color if false. It's based on what's happening on the first term and second term and the operation. Okay, so you just need to do it, just to read it this way. If first term equals the second term, then color if true will be put out. If the first term is not equals to second term, then color if false will be used as the out color here. So if they are not the same, let's make them not the same by manually typing in like this 1 here. You can see now the box immediately goes to -100. If you look at the value here, that's because now in the condition here, right, the first term is now not equals to second term, so the output R here will be reading the color if false value. That makes sense. And you can have other operations like greater than. Right. Now you can see it goes back again to 100 because first term 1 is greater than the second term. That's true, so the color if true now becomes the output color. So based on the condition of the first term and second term and the operation, based on if they're true or not, again, just read it this way. First term operator or operation, second term, in this case 1 greater than 0, right? That's true. So color if true will be passed on. And if 1 not greater than, maybe that's lesser than, you see it goes back to negative because 1 lesser than second term, 1 lesser than 0 is not true. So color if false will be passed out. So I just want to explain how this works before I use it. So I'm gonna rename this condition to condition left, back, leg, stretching. Okay, or actually stretch is how I name those guys. Okay, the first term, second term, then the idea will be I just need to know if the distance here as the first term. Okay, oops, let me try that again. Distance here to the first term, right? That's the arc length as the second term. I want to know that if the distance here is greater than or equal to the original leg length, if it's greater than or equal to the original leg length, then I want stretching, right? Because that's happening when I'm dragging it down too much. It will do that, stretching, right? And if it's not greater than, I'm just gonna make it 1 so that the color if false will be 1 and color if true will be this guy, output X, to the color if true R, this guy. and then the output color goes to the scale X. Oops. All right, now let's take a look. It's still stretching when I drag it back though. It stops stretching right away because in this condition here, the distance is getting much smaller. So here, the first term, the distance here is 100, but the actual leg length never changes because that's just measuring the length of the curve. And you can see that it's now, you know, smaller. So 100 greater or equals 155 is not true, right? It's not true anymore. So that color files will be passed on as the output are. Right here, right? Then that means, you know, 1 will be used for the scale X of those joints. Okay, so that's you know, some of the workflows I learned in my education, and I actually come up with another idea of making it easier. So we actually don't need to use the condition here, because if you really think about the problem, it's like we're not getting smaller than 1, right? The scale X will be always becomes bigger but no smaller than 1. So here, although this works, we can actually do another workaround, which is after the output X, we just simply clamp it. Okay, now let's clamp the length left back leg. Okay. And I'm gonna actually use that output X as input. Let me just clamp it. Maximum can be anything. Actually, the maximum should be the minimum will be 1. The maximum can be anything that you can put in a super big number, I guess. Or I can, if I want to keep it updating, I can maybe use that output X also as maximum. I'm not sure if that's gonna work properly, but yeah. So the output just goes to the scale X, right? So here you will see that the stretching, oh, it's still doing that, so I'm gonna do some changes. The minimum is 1, the maximum, I guess you cannot use that. It's just gonna use something like super huge that you don't really think that it's gonna exceed that, so that now you can see that it's not gonna go stretching in that much anymore. It's still gonna stretch out because, you know, we're basically clamping it to make it bigger than 1, more or less. Okay, so that's just another workflow or workaround that you don't need to use the condition and connect those guys and just use a clamping to get the value clamped. And you just need to have a super huge number there just to prevent it from doing that. Anyways, so yeah, that's gonna be another way that you can do this. It's probably gonna be simpler, but there is a limitation of this because this guy, you know, when you really want to be stretching that much, which never will happen, but just so you know that there is a limitation there. Anyway, so that's going to be another way that you can do this. All right, so that's basically it. That's how you do stretching here on the Aki. One more thing you may want to do though is that when you are stretching the leg and you're stretching back to FK, you see that the leg is still stretching. The reason being is because we're basically stretching the you know, the bending joint, and the bending joint stretching, or the scale X of the bending joint, right? It's not being controlled by the FK for now. Okay. So basically we also kind of like really don't want the FK to stretch in most of the cases. Maybe you want, maybe you don't, I'm not sure, but at least what we can do is we can actually disable it when we want it to. We can actually go ahead and do the add attribute here, and we're gonna do this stretch attributes, minimum to 0, maximum to 1, and press OK. And let's add the controller into the graph. Okay, that guy out. So I can just use this to control the you know, the input here using the stretch. I just need to use the blend color again, right? And the blender will be controlled by the stretch. Rename this blend color left back leg stretch, and the color 1 will be the output R from my clamp, and the color 2 will be just 1, and the output again goes to the scale X. Now if you go take a look of that stretching value, you can actually make it go all the way up to 1. Now it's stretching. If it's 0, it's not stretching anymore. Okay. And if you're in FK, right, you can of course just have the stretching if you wanted to by doing that, or you can disable the stretching right away on the slider. Okay, and that's gonna be it then for the stretching part of the leg. Let me actually go ahead and move everything back. Okay. Now we have a few nodes created. We can of course group them together. Let's call it left back leg stretching parts, and that can fall into the hierarchy of the left back leg. Right, so it's there now. Okay, and we want to go ahead and just hide this entire system because we don't really want to see them. Okay, so that it's organized properly. Okay. Alright, that's gonna be it for the stretching. Thanks for watching. See you next time. Alright, one last little thing we can do on the back leg is the volume maintain, which is after stretching, right? You probably wanted to keep the volume also, so that the volume will not just becomes bigger. The Y and Z scale of the joint will shrink when you scale the when you make the leg longer. Let's talk about the mathematics here. Let me go ahead and do some grease pencil drawing here. For example, let's say we have a cube like this. Right. Let's just assume that this cube. Let's assume that this cube, that its height is x, its length is y, depth is z, so that we know the volume v of this cube will be equals to x, y, z, right? Multiply those three dimensions together, you got the volume. Now let's then imagine that I stretch this cube vertically, just like how I stretch the leg vertically, right? It becomes longer. And let's also assume that this cube's volume is maintained, so that when I make the legs, the x go longer, for example, it becomes nx longer, n times longer, right? The y and z becomes, you know, somehow smaller. So let's say the y and z, their ratio now becomes, or their value becomes m multiplied by y and m times z. So that the y and z gets smaller. The m should be something smaller than 1, right? My and mz. Let's assume that when I stretch this cube into this shape, the length becomes n times longer, and the depth and the length and the depth gets m times as before, right? And the volume is still the same, so the volume will then the same volume here will then equals to n times x times m times y times m times z. Let's just assume that y and z gets shrinked the same amount. So let's say those two volumes are the same, and this nx and my and mz, their multiplication must be equals to x, y, z, right? So let me go write this guys down. Let me write those guys here. So x, y, z will be equals to n x, m, y, m, z, all multiplied together. Okay, now let's actually throw the x, y, z out. So that actually changes this equation equals to 1 equals n times m squared because there are two m's. Now you can imagine that so 1 over n will equals to m squared, so m equals to 1 over the square root of n. Okay. Now this equation shows us the relationship between m and n, which is how much x becomes, how much the length or the head, or how much the leg gets stretched here on the x direction, which is n here. If it does that much, then the y and z will become m, right? If x, the length, the scale x is n, the scale y and z should be m, and that's how you calculate m from n, which n is actually the scale x that we calculated already in the node editor. We just need to know what 1/_n is. Okay, if this equation makes sense to you, and that the volume will be maintained if you follow this equation here. So I'm going to go ahead and do that in the node editor. Actually apply the mathematical thing here. Okay. So before I think I can do that after clamping, right? The value we used for the the blend color, right? So let me first get the square root of n. In this case, n is actually what this output is, right? So I'm gonna do a multiply divide, and I'm gonna call this guy multiply divide left back leg and stretch square root. Okay, now I need to actually put the output r here, which is, again, if you look at the equation here, that's actually what n is. N is this guy here, the output r, and I need to know its square root. So I need to do that by go to attribute editor and change the operation to power and change the input to 0.5. Okay, so this means power input 1 by 0.5. Now we know that power by 2 means something square, right? Power by 0.5 is actually the square root. So this is basically the output here is the square root of output r. We can actually take a look at that. If I drag this leg all the way down, maybe 4 times longer, right, to there. And to take a look at the value here I'm getting, the input is around 4. Oh, it's too much. Go back a little bit. Let's go back just a little bit. Just a little bit, so that is really close to 4, right? 4.0. And the square root, the output x, should be 2. Let's actually see that. I need another multiply divide to do the second calculation, which is, I know underscore n now. I just need to know what is 1/_n, which is a simple division. I'm going to connect the output x to input 2. I can see input 2 is actually 2.02, right? And input 1 should be 1, and 1 divide that. Okay. Now you can see now this is actually power by 0.5 is actually the square root of the input of the input 1 here. So that's why I'm getting 2 here. I'm using 1 divide that. So 1 divided by the square root of n, which is the scale x, if that makes sense. Okay, so power and divide, that's what we do here. And the output again goes back to the color one we did for the stretching, for the stretch control. So when that is done, whoops, sorry, it's actually not there. What I was thinking, so that's not there. Sorry, that should be still reading the clamp, right? And it's the other two x. The other two, the output x should go to the y and z, because we're now calculating m, right? We're calculating m. M is multiplied to y and z to maintain the volume. Okay, then the output here. Let me disable the connection here. So the output will go directly to the scale, and it just passes to the scale down the way. Okay. Now you can see that the joint value is not only getting bigger on the scale x, it gets smaller on the y and z, so that the volume is maintained. And based on this equation, right, it should maintain exactly to the original volume because of the calculation we did with those two nodes. It's not complicated if you look at what we actually did. Just to multiply divide. The first multiply divide will have the original scale x as the input 1x. We power that by 0.5. And then the result goes to the input 2 of the second multiply divide. I'm gonna change this guy to multiply divide. Left, back, leg, scale, yz. And we're just calculate 1 over that to get how the scale y and z should be like, and the output goes to directly the scale values of the joints. So now the inverse scale is done. Okay, all right, so that's the scaling part.